I is not the only imaginary unit. In fact, there can be infinitely many imaginary units. Here's why.
We tend to think that I is the only imaginary unit. Why? Because it's introduced through the equation x squared equals minus 1. According to the fundamental theorem of algebra, this equation has exactly two solutions, I and minus I. So it seems there's no room for any other imaginary unit. But that's only true inside the complex numbers. Once we move beyond them, new imaginary units can exist. Complex numbers are two-dimensional because they combine one real unit with one imaginary unit. That idea is reflected directly in the complex plane. The imaginary axis is perpendicular to the real axis. Multiplying by I rotates numbers 90 degrees counterclockwise. I represents a completely new direction. Now here's a simple question. How many directions can be perpendicular to the real axis? As it turns out, the answer determines how many imaginary units can exist. We can imagine adding a new axis to the complex plane. Let's call it the j-axis. Like the I-axis, it is also perpendicular to the real axis. So it represents another independent imaginary direction. Its corresponding imaginary unit satisfies j squared equals minus 1. You might be wondering, aren't I and j actually the same? After all, both of them square to minus 1. But j is also perpendicular to I, so it represents a completely different imaginary unit. Now, our numbers consist of a real unit, an I unit, and a j unit. We've moved into a three-dimensional space. And we don't have to stop there. We can imagine another independent direction perpendicular to the real axis. The k-axis, then another, and another. We can keep adding independent imaginary directions forever. That means there can be infinitely many imaginary units. When there are many imaginary units, we use symbols like E1, E2, E3, and so on. Each imaginary unit squares to minus 1, and these units are perpendicular not only to the real axis, but also to one another. By using these different imaginary units, in principle, we can imagine a corresponding number system for each dimension. But adding new imaginary units creates a new problem. The problem is multiplication. The multiplication rules become difficult to define consistently. For example, in 3 dimensions, there is no consistent way to define the value of ij while preserving those properties. This is exactly what William Hamilton discovered. Instead of forcing a 3-dimensional system to work, he introduced a 4th dimension, creating the Quaternions. Only in dimensions 1, 2, 4, and 8, those familiar multiplication properties can be preserved. That's why those 4 dimensions are considered special. I is simply the imaginary unit of the complex numbers. Beyond them, you'll encounter infinitely many imaginary units. But you are the only one. Thanks for watching.